This work is done by under supervision of Pietro, Lenarda and Professor Paggi in IMT School for Advanced Students. I will go with the motivation behind the project, different viscoelastic material models, specifically for the viscoelastic materials, the numerical examples. Why viscoelastic materials? These materials are different because they behave differently during the different loading conditions. For example, if the materials are held at a constant stress level, it is observed that they start some creep. The strain is increases with respect to time. This behavior is basically called as creep. And if they are held at a constant strain, the amount of the stress which is required to hold the material at the constant strain goes on decreases with respect to time. So we are interested to study if there are the cracks are available, cracks are present in such kind of materials, how they are going to behave under the different loading conditions. Viscoelastic materials there are variety of examples. Sorry. There are variety of examples like in the discs of the spinal cord, they are basically viscoelastic. Then the polymer sponge, then 3D printed materials, and the metals at the higher temperature they show the viscoelastic effects. In our lab we have a Lexan FR25A. Is basically a backsheet material which is behave like a viscoelastic one. So we are conducting the several tests on that to study if there is a crack in that material, how it is going to be processed. So these are some samples. You can say these are motivation behind that. The study of viscoelastic materials is basically called as the rheology. In the rheological sense, in the rheology there are variety of the models are described based on the combination of the springs and dampers. The spring is basically to take care of elastic part, and the damper takes the differences in the strain region. The basic model is like sigma t is proportional to the rate of strain, like the damping effect. But in our formulation we are restricted to the linear viscoelasticity. It is basically seems that the strain is in proportional to the stresses. The more general form of spring damper series is basically the Prony series, in which it is generalized form is shown in the shown here, like there is a stiff string and they are in parallel with the different combinations. In this way the elastic relaxation or elastic modulus changes, and we have like the parameters like EI and tau I is basically the damping time coefficient and the elastic modulus of a spring. These are the unknowns. In total there are 2n plus 1 unknowns. But recently, Professor Paggi and Lenarda implemented the fractional calculus based model for the viscoelasticity. The model is working quite well for the materials, and here we have only two unknowns like A and alpha. With the tuning of this parameter, where the alpha is changing from 0 to 1, we can get the equivalent elastic relaxation response. So here this is starting from our weak formulation and the generalized form, and you can see that if this parameter takes the previous time step and the history, depending upon the history of the strains, we can calculate the current deviatoric stress, and then we can combine together to get with the volumetric stress to get the current stress in the material. Similar in the fractional calculus model, the sigma is basically the fractional derivative of the current strain, and for any fractional derivative can be given by this function, and by using the Granol approximation we can calculate the displacement values at n plus 1 stage, where the Cj's are basically the coefficients which can be obtained from the recursive formulation. So once the model formulation is there, so we try to implement this for the simple case where the simple rectangular structure, which is nothing, the bar which is loaded with this profile, which is held at a constant stress level of 3.5 MPa for duration of a time, and how it is going to behave with both the models. First, I have considered that if it is a Prony series, I consider there are two value of shear relaxation modulus and the time periods, and based on the curve fitting, I find out the value of A and alpha which are there. Now both the models are giving the perfectly good response together, and you can see for the creep response, this is the response of creep, and this is for the relaxation of the material, which is obtained at a strain level of 0.0833. The both models are working perfectly fine. Then we went for some experimental test on the FR25A. For this, I obtained first the relaxation at the 450 newtons. This is the graph. Then I curve it with the regression to get the value of A and alpha. And once I have this A and alpha ready, so I can go with the phase field modeling, the parameter distribution. I can go for phase field. As everybody knows that phase field is basically a representation of discrete crack into the smear event, where the 0 is basically unbroken, and if the phi is equal to 1 is basically the crack, it is the broken sample. So this is a total strain energy, and we are degrading this strain energy with the degradation of 1 minus p square. This is 82 model, and I am using basically here the volumetric and derivative speed, and my fractional energy can be given by this function. Okay, this is the big form, and after the functional can be and this is the energy. We can say the crack driving functional can be given by this, and the if I get the residues after the variational formulation, after finite discretization, we can get the residues, and then we can go with the FEM, and to get the KUU, the stiffness matrices can be formed, and they can be solved using the staggered scheme, and we can solve the problem. Similar with the fractional calculus model, here the derivative and volumetric they are sigmas are split into two parts, and they are again combined together 2 by 3, and we are calculating the fractional model, and the same the displacement at the next stage can be given by the recursive formulation, and the CJs are basically coefficients. It is observed they are in such a fashion that they are they are more priority is given to the previous stage as compared to this one. So they are also history dependent, and we are considering the history. I try to solve the simple ACN sample which is having the edge crack, which is the 500 mm. The 500 mm is the dimension of this specimen. The parameters are taken from the paper. There are 5 Maxwell chronicity I have considered, and after the parameter fitting from in the log basis, we can calculate like this is a time distribution in the log time distribution. We can get the parameters for the fractional calculus model, which are given there. I tested this sample. This is a numerical experiment I tried with the reducing the loading rate. Like first I considered the 50 mm per hour, 20 mm per hour, and 5 mm per hour. It is observed that as the loading rate decreases, the peak value or the peak forces are going on decreasing, and so it is because that the material is loaded with the lower loading rate. The material believes some relaxation inside it, and therefore the forces are dropping. So we wanted to see that same in the case of the experimental campaign. Here the loading rate are basically 0.1, 0.2, and 0.001. You can say that the similar kind of trend can be observed. If the loading rate is higher, the higher is the peak, and if we are reducing it, the peak load are decreasing. So, but these are still under process. We have to carry out more experiments to calculate GC and LC. So we are working on that. These are my references. Any questions?
Yeah, thank you very much, Ajinkya, for that nice presentation. Are there questions?
Yeah. Okay. Yeah.
How did you explain how did you obtain the maximum parameters mu and
Okay. In the paper they have considered only 3. Then I wanted to have I wanted to study the effects of the more time effects or something. So I added these parameters accordingly. So this is like a numerical experiment of a single AC. They are given now. Like in the paper, I have to try it. So I made these parameters. Like I have taken this. Okay. We can sorry.
okay, we can
Yeah.
Thank you very much for your talk. If I understood correctly, you considered in your energy functional only an elastic part of the
Elasticity,
free
yeah.
energy.
Yeah.
Is there a specific reason? Or is it
I'm
just-
considering that the viscoelastic energy is coming from the strain energy. So if I change the strain energy model into the viscoelastic part, so I will get the whatever the results I want. I also wanted to check the effect of GC with the strains also.
Yeah.
That can be one reason. Then LC also. During the numerical experiments we are doing in the lab, if I want to, depending upon the curves I will get, depending on I will change to modify it accordingly.
Yeah.
So that is the.
Thank you.
Yeah, maybe I have one question also. So you are using that method to describe the strain-independent stress at rupture in a way.
Yeah.
You also have a focus on pre-rupture maybe?
Yeah. We are also doing some experiments on the flip rupture.
On the pre-rupture.
So that,
Okay.
that is where the reason like clip and the glutamic possibility.
Okay. So then thanks again for your presentation.